This is the y-axis, this is the x-axis. And we know this function looks like this. It comes up past the y-axis, it just drops down. 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, 1 over x. When you get up to 100, 1 over 100. When you get to millions, 1 over a million. It's getting closer and closer to 0. It's never quite getting there. So that's the function, 1 over x. This function has no closed form. The summation of 1 over I from 2 to n does not have a solution. Okay? It's not geometric. It's not one of our fancy summations that we can cancel out. It doesn't have an exact solution. But we notice that if you look at the dots, this is 1 over 1, 1 over 2. The dots is a discrete function, right? If we look at the dots, we notice the function is strictly decreasing. Getting smaller, smaller, smaller. As it goes to the right, it's getting smaller, strictly decreasing. So if I'm looking to get an upper bound for it, and notice I'm looking from 2 to n, so I'm really looking at this box. This is the first one. This box, all the way up to some n value, last box. So it really ends at n plus 1, right? It really does. But because it's decreasing, notice that if I start my integral at 2, it's going to be bad. That will not be an upper bound, because as soon as I start at 2, which is the same as this index, the decreasing function is getting smaller. So I have to back my integral and start it at where does my integral have to start? It has to start at 1. Because what I'm going to do is I'm going to say the area underneath the blue is more than this rectangle area. Under this blue is more than this. Under this blue is more than this. So my integral, even though I'm going from 2 to n on the discrete, in order to get more than this area, I have to go back to this guy right here. So therefore my integral is going to go from 1 to n. Notice that I go down here, I don't move this, because 1 to n is the same width. Because if it starts at 1, it ends exactly at n. This one starts at 2 and ends exactly at n plus 1, because it's discrete. Discrete always has that extra 1. Okay? So once I do that, then I have the integral of 1 over x dx. But we know from the notes I just gave you today, or you may know from your other studies of math, that the integral of 1 over x dx is natural log of x. And I'm asking you to evaluate ln x from 1 to n. Therefore, it's going to equal to ln n minus ln 1. And you already know that ln 1 is 0, because e to the 0 power is 1. Therefore, the answer is ln n. So this is a very remarkably cool result, because what we have is we have a summation that we can't solve, but we know that the summation is bounded by ln n. So that means if I go, for example, so let's say I wanted you to take the set of values, let's say this one right here. Let's say we're going to take some values. Summation as I goes from 2 to, let's say, 7 of 1 over I. Of course, that's going to be 1/2 plus 1/3 plus 1/4 plus, and final one is going to be 1/7, right? And if I had 17, plus, 1 over 17, right? So, and of course, I could change this. Instead of 17, I could put 17 million or 17 billion. Now you got a lot of work to do. So I don't know what the answer is going to be, but I know that this will be less than the integral from where? From 1 to, let's call it 17 here, 1 to 17. So we back up from this index, keep this one the same, of 1 over x dx, which is equal to, this is equal to natural log of x evaluated from 17 to 1, which means it's equal to log 17 minus log of 1, which is log of 17. Now, I don't know what log of 17 is, but my calculator does. So I'll just type in 17, natural log, boom. It's about 3.1, 3.2. I know that the area of the rectangles is going to be less than or equal to that. between friends, it's going to be a little bit less. Mathematically, less than or equal to. You understand what I'm saying? I can see it's going to be less. You know it's going to be less, but mathematically say less than or equal to. So we have now found an upper bound for a summation that has no closed form. So that's why integrals are important for us, because they help us solve this kind of problem. So I have to give you this confusing slide here. So this is just, so here, what I'm asking you to do, to find a lower bound for LGI. Now what is LGI? LG is log base 2. Log base 2. So before you start finding lower, now first, so let me just tell you another story. There is no closed form for LG. X. There's no closed form for that either. First summation of a bunch of LGs. So what we have is we can use an upper bound. Before we start using our integrals, let's remember what the function LG looks like. So this is y is equal to LGI. Log base 2 of I. So what are some LG values that we can calculate nicely? How about LG of 1? What's that equal to? That equals to 0. How about LG of what? LG of... What's the next one we're going to try? 2. What's LG? Base what? It's 2, right? So LG of 2 is going to equal to what? 1. What's another nice number? LG of 4 is equal to 2. Because 2 to 2 is 4. Let's do one more. LG of 8 is equal to 3. So what happens is, so these are, here, these are the x values, these are the y values. This is the function, this is the variable, the dependent variable. So, so if you look at the, so we have 1, 2, 3, 4, 5, 6, 7, 8. And then we have 1, 2, 3. So the function clearly, when x is 1, it's 0. Okay? When x is 2, it's 1. When x is 4, it's 2. And finally, when x is 8, it's 3. So you can see the function looks like this. Okay? All log functions look like this. Some are a little bit smoother this way, some are right a little bit more, but they all have that general shape. All of them. Same thing with ln. Same thing with log base 3, log base 4, log base 10. They're going to look a little bit different. They may grow a little bit slower, a little bit quicker, but they all will start slowing down immediately. But what kind of function is it? Is it a decreasing function or increasing function? It is an increasing function. So therefore, if it's an increasing function, and we are looking for, it's an increasing function, we're looking for the lower bound. So should we start at A, or should we back it up? If we have to back it up. We have to back it up, because it's increasing. So if you start at A, from A to A plus 1 will be already more. So it's going to be an upper bound, not a lower bound. So the upper bound will go from A to B plus 1. And the lower bound, just shift it over 1. A minus 1 to B. Okay. Awesome. You guys are a great class. Very quiet class, but a great class. Nonetheless. All right. All right. So let's see what we have. So keep in mind that what we're going to do, so there is no closed form for this. So this is what we really want. I'm also showing you, notice that LGI from 1 to n is the same as 2 to n because LG of 1 is 0. Fine, fine, fine. So LGI from 2 to n, we're going to back it up. The 2 is going to get backed up to a 1. Leave the upper index the same. And we want the integral of LGX dx. Now, you saw, this is the tricky thing. The integral of LGX, I didn't give you. I don't have to give it to you because you know that you can change the base of LGX. LGX, I love this. I have to do this continuously. I know it'll work. So LGX is equal to natural log of x divided by natural log of 2. So therefore, the integral of this is equal to the integral of this. And the integral of the right-hand side, this is a constant, this is a function, will be equal to the integral of natural log of x times 1 over natural log of 2. So whatever you get, you're going to divide it by the natural log of 2. And you know the integral of x ln x, of ln x is going to be x ln x minus x, which is divided by natural log of 2. So just a little bit of mathematics there. But that's why I gave you the integral of ln x. Now, in a real math course, you might have to take integrals of complicated log functions. We don't have to do that. Because as you're going to find out, we can simplify all our functions to the very basic functions, which are called complexity. And work with complexity makes it to the point that we're going to be using very simple functions with not complicated coefficients. So there's not a lot of things to worry about. So, in this particular example, you can see that I'm changing the base. So therefore, the integral of LGX is LGE times ln x dx. Okay, the LGE is just a constant, it comes out. The integral of ln x dx is going to be x ln x minus x times LGE. You evaluate it from 1 to n. And you can go through some of the mathematics here, and basically we're going to get that the summation of LGI from 1 to n, which is the same as from 2 to n, is greater than or equal to n LGN minus 1 5 n. It's a very, very useful result because we weren't able to solve it before. Okay, so that kind of completes that set of slides. Any questions about this? That is as hard as the math is going to get. You might have to do a little bit more of it, but that's basically the idea. So what we're going to do now, let's go to the next set of slides. And I will talk, let's see if I can get to this. These are from the textbook lecture notes, and these are available. I'm going to skip this one right now. I'm going to go to lecture 2. Okay, so what we're going to do is we're going to look at something called asymptotic notation. Asymptotic notation is basically trying to distill and simplify the actual complexity or the instruction count to as simple function as possible. So really what we do is we concentrate on the characteristic operation, and then we strip it of any coefficients, just leave it. So if the characteristic operation occurs 6x squared times plus 18x minus 3, we just say forget about the minus 3, forget about the linear, let's worry about the quadratic, forget about the coefficient. It's x squared. We strip it down to as simple as that. Why? Because what happens is, as x is getting bigger and bigger and bigger, that x squared term is the one that really drives the function. Everything else becomes very, very small by comparison. So the function without those pieces and the function with those pieces, if you graph them together, are almost the same as we go further and further out to large values. Does that make sense? Yeah? So that's the idea. So I will have more to say about this. So these three notations that you see here, these notations are called big O notation, big omega notation, and big theta notation. We will also add some more, which is going to be the little o and the little omega. There is no little theta. It's big theta or nothing. So big theta is the important one. Okay, so let's figure out a little bit of how that works. Actually, you know what, I'm gonna back out of these notes for a second, I'm gonna come back to them. So I wanna show you another set of notes that I developed. And that's going to be the notes on the asymptotic notation, which you also have, of course. Okay, so asymptotic notation. Hopefully this is correct. Okay, so these notes are nice and easy, which is very popular with students. So it's like that notes that are easy, not complicated. So asymptotic notations allows us to compare the complexity of a given function to a known complexity. Okay, what does that mean? Well, we may know what x squared looks like. But if a function is got x squared in there, but other linear terms and other constants and other coefficients, it's too complicated. So we're going to just say, let's just worry about what we have. And we can show by using limits that this is actually the way to do it. So we're mainly interested in growth of functions as x is getting larger, is increasing. So big O, big omega, big theta. It's just Greek letters. Okay, so in general, I want you to think of big O as an upper bound. It's not strictly true, and I'll differentiate what I mean by that. So it's basically an upper bound. This big omega is basically a lower bound. Again, not strictly, but that's what you're going to think of. And big theta is the proportional bound. The best notation for a function that we can have, if we can have it, is big theta. Because in a sense, big O is telling you, this function is no bigger than this. Okay. No bigger than this. Is it no bigger than this? I don't know. Is it no bigger than this? I don't know. It might be. It's no bigger than this? No. This. So it tells us an absolute upper bound, but it might not tell us exactly what the function is. Could the function have a big O up here, but have an actual theta down here, much smaller? It's possible. So why don't you tell me the theta? Why are you giving the big O? Because the big O is easier and the theta is complicated. So I know this is going to guarantee, this is a guarantee, but I can't figure out how to do this. Okay, reasonable. Okay, so the other notations we're going to have is the little o and the little omega. So the little o and little omega are going along. So this is big O, little o looks the same except it's smaller. And then big omega looks like this, little omega looks like a funny W. Actually, little o and little omega are better than big O and big omega. They're more powerful, but nobody talks about them. Again, they're a little bit tougher to get sometimes. So little o is what we call a strict upper bound. Strict upper bound. If a function is little o of n squared, it means its instruction count is slower than n squared. How much slower? Well, it's not 1/8 of n squared. It's no n squared at all. It must be of lower complexity. And the way we're going to be able to do that is we're going to be able to take the limits of these functions to see where the functions go as n is increasing. The omega, little omega, gives you a strict lower bound. So if you get a strict lower bound, that means your function will be more costly than this one. How much more costly? Well, we don't know. But it's going to be more costly. So that's better than just saying, big O says, well, your function is n squared, big O. What does that mean? Well, it could be big O. It could be log n. It could be n log n. It could be square root of n. I see. Well, what is it? Well, we don't know, but it's big O of n squared. So n squared doesn't give you a lot of precision. It says it's no worse than this. Could be this, could be less. Big omega says could be this or could be worse. Theta says it's this. Theta is so good, it just says this. So if your function is n log n, guess what? It's n log n. Could it be n squared? Nope. Could it be n? Nope. Could it be square root of n times n? Nope. Okay. So what we're going to do is we're going to take these functions. So this is the known function. Let's say we know the known function is n cubed, and this is our function of n. We will take the n, which is the data size, the input size for the function, and we'll put the ratio of our function that we're interested in over a known function n cubed, and then we'll take the limit as the data size goes towards infinity. Now, if this limit converges to a constant c, that means that as n goes to infinity, these functions are proportional to each other. And c is the proportionality constant. If this limit goes to 0, which function do you think is growing more quickly if the limit goes to 0? The bottom. The bottom goes, because the bottom is driving n cubed. If it drives it to 0, it's just dividing it so quickly, as then it's increasing, then it's going to 0. That means that the function on top is growing more slowly than the function on the bottom. In each case, whether the limit goes to constant or goes to 0, in either case, the function f of n is an element of the set of functions that grow no faster than n cubed. So big O of n cubed is a set of functions that grow at the rate of n cubed or slower, no faster than n cubed. That's what this set of, so f of n is an element if these two things happen. And this tells you what the interpretation is if c is, if it's c or 0. So let's look at an example. Let's say we have two functions, f and g. F on top, g on the bottom, and we let n go to infinity. Let's say the limit goes to 0. Which function is growing more quickly? Top or bottom? Bottom. Because going to 0, this is growing more quickly, driving, getting bigger and bigger and bigger, making the whole thing go to 0. So, therefore, we would say, if this is equal to 0, then f of n is an element of big O of g of n. This is growing faster. That means this function f of n is growing same rate or slower. That's true. We know it's not the same rate, because if it was the same rate, we would get a what? A constant. So therefore, we know it's slower. But as far as big O is concerned, this is still a true statement. This is saying f of n grows at the same rate or slower than g of n. That is a true statement. A better statement would be to say f of n is an element of little o of g of n, which says this function is growing slower than g of n. That's a stronger statement. So little o allows us to say it's slower than this one. Because we know it is with a 0, but big O doesn't tell us that. So it would be stronger to say little o of g of n. The bottom two, we're just flipping them around. We're saying if g is growing faster than f of n, then f of n is growing slower than g of n. Therefore, g of n is growing strictly more quickly than f of n, because this is a strict lower bound. That means that g of n is more quickly growing than f of n. And this one says that g of n is growing at the same rate or more quicker than f of n. So I just flip them. Any questions on that? Okay, so let's say the functions, the limit of the two ratios go to a constant. So in that case, if they go to a constant, we can say that f of n is big O of g of n because it's growing proportional or slower. It's proportional. And f of n is an amount of big omega of g of n because it's growing proportional and faster. It's proportional. And then this is the best one to say f of n is proportional to g of n. This is the best. These are also true. Let me ask you a question. Would it be correct to say that g of n is an element of big O of f of n? Yes. And would it be correct to say that g of n is an element of big omega of f of n? That would also be true. What do you think it means if f is big O of g and g is big O of f? What would that mean? If two functions are big O of each other, what does that mean? That means that one is growing less or proportional to the other, and the other is growing less or proportional to the other. to the 1. So what does it mean? Could there be a difference in complexity of these two functions? Are they really proportional? Could they be lesser grower and faster and slower? No, because faster and slower would be okay for big O in one direction, but it wouldn't be okay for the big O in the other direction. So if they're both big O of each other, that means proportional or slower, proportional or faster is just proportional. So if two functions are big O of each other, that means they're proportional to each other. So you can show if this is true, if f of n is big O of g of n, if g of n is big O of f of n, then they are theta of each other. They're proportional. Let's say the limit of the ratios go to infinity. If the limit goes to infinity, what does that mean? It means that the function on top is growing more quickly. It grows more quickly. Well, that's fine. So this is nothing more, if you think about it, this example is the same example as we just had a second ago when it went to 0. It went to 0 because what was growing more quickly? G. So if I flip G on top and F on the bottom, what would that go to? Then it would go to infinity. So therefore, this is nothing more than the reciprocal of the other example. And so just think about it logically. If the limit goes to infinity, this grows faster. And therefore, if F grows faster, then we can say that G is an element of little o of f of n. That means that G is growing slower than f of n. And this says G is growing proportional or slower. Yes, it is slower. Or proportional. Yes, it is or proportional, but it's really slower. But it is or proportional. Okay? So therefore, this is just saying G is proportional slower. G is definitely slower. This says that F is definitely, it's the strict lower bound. So that means F is definitely faster than G of F. No, faster, by the way, means bad. It's bad. Because faster means higher complexity, right? Growing faster, bad. We don't want our algorithm's complexity to grow faster. We want it to grow slower. But this says, so therefore F has a strict lower bound of G of n, so F is strictly faster than G of n. And here we're saying F of n is proportional to G of n, or faster. So again, these are stronger statements. The little omega, little o's are stronger statements. And that's all I'm saying here. This is sort of puts everything together. These are the little guys. Little o, little omega. So let's give an example. Now, there is a little rule in calculus that we can do which helps us evaluate complexities when we can't do them in an easy fashion. And it's called L'Hopital's rule. And let me make sure you understand when it applies and why it's so popular in computer science algorithms. What happens as n, the problem size of an algorithm, goes to infinity? What happens to that function? As input is increasing, what's happening to the function? It's going to be increasing. More instructions, right? So the higher the input into an algorithm, the higher the output. So the limit as n instructions, the number, the data size goes to infinity, as n goes to infinity of a function of n, it's going to go to infinity. How about another algorithm? It's also going to, all algorithms go to infinity. If they didn't, we'd solve all the world's more difficult problems. But unfortunately, our algorithms, as our input is increasing, get harder. You know about it. You know that bubble sort, even bubble sort. It had, something like n squared instructions. One of them had 3.5 n squared, another one had 2.5 n squared. But we know when n is 1,000, that's 2.5 million. And when n is 1,000,000, it's 2.5 trillion. So the number of instructions is going up like crazy. So algorithms, as n goes to infinity, go to infinity. Well, L'Hopital's rule just loves that. Because basically it says if you're taking the ratio of this function, and it is going to infinity, and this one is also going to infinity, then the limit as n goes to infinity is going to equal to the limit as n goes to infinity of the derivatives of the functions. Because what's a derivative after all? A derivative is the rate of change. Okay, so let's quiz on derivatives. What is the derivative of e to the x? E to the x. What is the derivative of x squared? 2x. Okay. Not too hard. Right? So, let's look at the curve e to the x. And instead of making e, which is 2.71828, instead of using 2.71828, how about if we just use 3? It's a little faster than e to the x. So, and the derivative of 3 to the x is 3 to the x times natural log of 3. On the nose. So if you, but the derivative of 3 to the x, you have to remember, is really 3 to the x times some coefficient. So it's proportional to 3 to the x. So the derivative of any exponential is proportional to the original function. So let's think of 3 to the x, and the derivative is, I'm going to just simplify 3 to the x. And then x squared, the derivative is 2x. Let's look at these two functions as x is equal to 5. So let's evaluate the derivative of 3 to the x, that's 5. The derivative of 3 to the x is 3 to the x, which means at 5 it's going to be 3 to the 5th. That's 3, 9, 27, 81, 243. What is 243? 243 is the slope of the tangent line at 3 to the x when x is equal to 5. That function is just going up like crazy. So 243, you know what the slope of 243 is? It's steep. That's 243 up, 1 over. That's the rise of a run, right? So it rises 243 units to a run of 1. Okay. What about the function 2x? What about the function x squared? The function x squared has a derivative of 2x. 2x with 5 is 10. The slope of the tangent line at x squared at x equals 5 is equal to 10, which is steep. But it's not 243 steep. And what happens as both these functions continue going to the right? That e to the x, or 3 to the x, is getting steeper at a quicker rate than the x squared function is getting steeper. So what we say is that 3 to the x is approaching infinity at a higher rate than x squared is approaching infinity. They're both approaching infinity, but one is at a higher rate. So if you put them over each other, and you take the limit as n goes to infinity, they both try to drive to infinity. But look very carefully. This function drives to infinity, tries to pull the ratio to infinity. But this function, which is going to infinity, is trying to pull the ratio to what? To 0, because when this is growing, the whole ratio is getting smaller. If I'm going to infinity, the ratio is going to 0. If I'm going to infinity, the ratio is going to infinity. They're fighting each other. Who wins? The one that has the higher rate of change. And L'Hopital's rule says, find the rate of change of this, find the rate of change of this.